All right, welcome to the Computer Science Department Colloquium. Be introducing Raf. I think Raf probably doesn't need much of an introduction. So all of you, excuse me, hello. Can I throw spitballs at you guys? Most of you know Raf. What you may not know about Raf is actually he's a very serious and accomplished chorister. And so when you hear his deep voice, you'll understand a little bit more about where it comes from. Before Boulder, Raf did postdocs at Harvard and Microsoft Research in New York. He got his PhD in computer science at Berkeley, advised by Christos Papadimitriou. Right? And his research falls at the interface between theoretical machine learning and economics. And he'll tell us a lot more about that over the coming 50-ish minutes. And I'll leave it to you if you want questions in line or afterwards.
Oh yeah, questions during are fine. Yeah, thanks Liz for the introduction. And thanks everyone who's in person and online. Yeah, so I thought I would start off by giving you an overview of what I've been thinking about for the last 8+ years at CU. And at the center of all of these problems is this area of information elicitation. And like a core problem, or like a classic problem, aside from clicker problems. Hold on. Oh, I think I know what's happening. There we go. Yeah, so like at the center, like a classic problem in information elicitation is the following. So you have some agent with some belief about some future outcome, say the probability of rain tomorrow. And you would like to ask this agent to make a prediction. But of course, this prediction may differ from what they truly believe. And so you would like to design some score, which you can think of as a payment to the agent, which will depend on both their prediction and the eventual outcome that you can observe. And you want to design this score in such a way that if the agent is trying to maximize the expected score, and from their point of view, the outcome will be drawn according to what they truly believe, then in doing so, they will realize that the optimal thing to predict is in fact what they truly believe. And if you can design such a score, we call it a proper scoring rule. Bo talked about them a bit in his talk a couple of weeks ago. And there's a nice literature about how to design them and so on. And what's interesting is, despite the very economic nature of this problem that I've posed, it turns out to be exactly the same mathematics that's going on behind loss function design and machine learning. So here, instead of maximizing a score, we're minimizing a loss. And instead of taking an expected value according to a belief, instead we're sort of taking expected value according to the empirical distribution from our data set. But up to these details, essentially the same object is showing up in both places, up to a minus sign. And this dual role of scoring rules and loss functions drives a lot of the work that I've been thinking about. So loss functions at the center, you could think of them as a learning objective in machine learning, or you could think of them as a contract or a mechanism in economics. And it's really the same object floating back and forth. And that drives a lot of the work that I've thought about in this area. So there are lots of topics that kind of float around this dual role. Don't worry, we won't talk about all of them. As the title suggests, I'll focus the talk mostly on this problem of forecasting competitions, which I think nicely sits right at the interface between machine learning and economics. And in fact, we'll see that the solution to the particular problem in forecasting competitions also solves a problem in the design of learning algorithms that are robust to strategic manipulation. So those two together will form about the first 30 minutes of the talk. And then towards the end, I'll very briefly tell you about some work in decentralized markets and learning in games. So that's the plan. All right, let's do this. So, all right, forecasting competition. So this is joint work with PhD students Anish, Mary, Melody, undergrad thesis student Robert, Bo, who we all know, and Manuel Ladser from Applied Math, Courtesy, and Computer Science. And I'll tell you about mainly the first paper here, which was published in the Conference on Economics and Computation 2021. So that's like the flagship conference in this area. It's also a conference that Bo and I hosted here at CU last year. And towards the end, I'll tell you briefly about some follow-up work as well. All right, so what is a forecasting competition? I mean this quite broadly. So if you've ever participated in or heard about a Kaggle competition, that counts as far as I'm concerned as a forecasting competition. There are also, so Kaggle, if you don't know, is a platform that hosts large machine learning and data science competitions, as well as lots of other things. There are also others like the Good Judgment Project and so on that focus more on geopolitical forecasts. But at a high level, forecasting mechanism we can think of like this. So there are n different teams or forecasters, as I'll call them, that are each submitting predictions about m different events. So you could think the probability of rain 4 days next week. And so each forecaster makes a prediction on each of the events, and then you eventually learn the outcomes for each of these events. So that the outcomes, in this case, whether it rained or shine, you eventually observe that. In the case of geopolitical forecasts, that observation could be many months later, but to close the competition. But in any case, once you've observed these outcomes, then the mechanism would like to choose a winner of the competition. Okay, so how does one choose the winner? Well, it's something that we call in this paper the simple max, but it's the thing that you would naturally do. So you take each forecast and each outcome pair, and you use a proper scoring rule to score them. And then you total up all the scores across all the events for each forecaster. And the forecaster that has the highest total, you declare the winner of the competition. So this simultaneously is very reasonable, and it seems quite justified. You're using a proper scoring rule. They're sort of designed for this stuff, so no problem, right? Well, it turns out that despite the fact that this mechanism is not only reasonable, but is the most common, so all of these platforms use this mechanism, turns out that there is a fundamental incentive problem with it. And we can see that problem with the toy example. So suppose you had a competition that only had one event, and there are 3 forecasters. And suppose the correct probability, in this case of the rain tomorrow, was 50%. And there are 3 submissions, 10%, 50%, 90%. So the forecaster in the middle is totally correct, but there are these other bozos that are saying wildly incorrect things. So what's the problem? Well, I haven't told you what proper scoring rules are, but it turns out they satisfy this monotonicity property that the higher the probability that you assign to what actually happens, the higher your score. That's not sufficient, but it's necessary. So let's think about what happens when it rains. Well, the middle forecaster doesn't win in this case. Instead, it's the 90% forecaster. They're looking pretty good. But if it doesn't rain, then the 10% forecaster wins. So deterministically, no matter what happens, the middle forecaster, who is completely correct, cannot win this competition. And, so what does the middle forecaster have to do? Well, they would extremize their prediction. So they would move it close to 100% or 0%. And they'd accept the fact that they would only win with 50% chance. Now you might wonder, okay, this is a very simple toy example. There aren't competitions with just one event. Does this happen in real life? And it turns out, is a question?
Sorry.
Yeah.
Can you say more about what it means for 50% to the right answer?
Yeah.
I'm lost.
So yeah, so this is we could get into the philosophy of what probability means, which is unfortunately very adjacent to that question. But imagine I had a fair coin, like I was just flipping a coin. So we would all agree that the correct probability should be close to 50%. Maybe Jim doesn't. Does that make sense though? Like, yeah, so in some sense, who knows what the correct probability is, and this is what's driving a lot of the nonsense in political punditry that people always can explain what their predictions were. But in a world where it was the correct probability, that would not win this competition. So it turns out this does show up. Oh, and I should say, yeah, so the issue, what is the problem here? Well, as I mentioned, proper scoring rules are designed under the assumption that the agents will maximize their expected score, which is not happening here. What's happening is agents are trying to maximize the probability that they win the competition. And it turns out that that subtle difference in the incentives is what's driving this problem. Okay, and so it does show up in real life. So Kaggle ran a March Madness competition in 2017, and the winner of that competition, Andrew Landgraf, wrote this very interesting blog post about how he designed his submissions. And you can see that, you know, in his little flowchart here, there's the usual stuff you would expect. There's some basketball data, there's some brackets, models of basketball games, but then there's all this other stuff. So Andrew explicitly took data about other submissions, modeled the submissions, and simulated, basically trying to figure out what are people likely to also be submitting, and how can I best respond to that? How can I, given what other people are going to be saying, where do I need to be more extreme and less extreme to maximize my chance of winning? And, you know, you could ask, what is the problem really? Well, one of the problems of this showing up, of people like Andrew doing this kind of stuff, is it's not really clear whether you're picking the best forecaster. And here we're sort of getting back to Jim's question about what even is best forecaster. But if you consider that there are some true probabilities out there, you would like to pick the forecaster whose beliefs match to true probabilities the closest. But here, like, whatever Andrew's model of basketball games said to predict, that's not actually what he's predicting. So there's this difference between, you know, what the model says and what is actually being submitted to the competition. So you can't really be sure that the winner of the competition is actually the best forecaster in this sense. And that's what I'll be focusing on for the talk, is how can we guarantee that the best forecaster is chosen with high probability? There are also other problems like wasted effort. So you would like your forecasters to be spending their time on, you know, modeling the whatever is going to be forecasted instead of spending all this time strategizing, and a sort of time taken away from improving their model. Okay, so here's basically the problem. And when we started thinking about this problem, there was a very interesting solution proposed already called the Event Lotteries Forecaster Mechanism, or ELF for short. And here the idea is to, for each event, you assign a point to a forecaster at random using some lottery. And you design the lottery carefully so that it's biased towards the higher scores. But it's not just give the point to the highest score, you construct this lottery. And then at the end of all the events, you see who had the most points, and then that's the winner. So it's like, you know, instead of totaling up scores, you're sort of assigning a point at random with a lottery, and that's the score for that round. And it turns out that it's actually somewhat subtle to prove this, but it's truthful. So the optimal thing to maximize your chance of winning is to report exactly what you believe. So it has that nice property. And it's also accurate in the sense that you can prove that it picks the best forecaster in the sense that I mentioned before, that the beliefs best match the true probabilities, with high probability when you have enough events in the competition. And how many events? Well, n squared log n events, where n, if you recall, is the number of forecasters. Well, it turns out you can improve their analysis. So we got rid of the square. So we got it down to n log n using a different concentration inequality. But we also showed that this is tight. So ELF really does need n log n events. And you can see that basically there's enough randomness, enough variance in these lotteries that even if you had a perfect forecaster against n-1 terrible forecasters, you would still end up choosing one of the terrible forecasters until you had about n log n events. So I don't know, maybe that's good enough. Maybe there's no work to do here. How good is n log n? Well, it turns out if you go back to that March Madness competition, there were 442 forecasting teams, but only about 63 events. So this is theory. This is big O. I haven't told you the constant here, but yeah, it's not that good. You know, so n log n is way more than 63, even when you plug in this constant. So if you ran ELF on this competition, it would be very random, like close to uniform. So that's not great. So the central question that we wanted to answer is, could you design a mechanism that picks the best forecaster with high probability using fewer than n log n events? Let me pause here. Are any questions on the setup? Yeah.
Does the constant depend on true probabilities? And also, like if you have very rare events.
No. The constant doesn't depend on the probabilities. And essentially it's because the definition of how good a forecaster is also depends on the true probabilities. So yeah, oh, I should mention, so when I say I'm kind of glossing over the usual epsilon delta stuff that goes on here. So when I say pick up the best forecaster, implicitly there's an epsilon that says I want a forecaster that's within epsilon of the best. And that epsilon also shows up in this bound. So I think maybe that's what you're thinking about, that if there's like a very small gap between the best and second best, how could you possibly choose the best? And the answer is we're okay with choosing the second best if they're also epsilon good. Other questions?
There's one from the chat. Do
Okay.
events have binary outcomes?
Ah, great question. So for now, we can say, yeah, let's say that events for the talk have binary outcomes, but you can extend it beyond that case. And another assumption is that the events are independent, and I'll get back to that assumption later. Okay, so another thing to mention at this point is that the best possible bound that you could hope for in terms of the number of events that you need is log n. So this comes from classic PAC learning theory lower bounds. It's not totally immediate, but you can adapt into this case. So we know that somewhere between log n and n log n is the correct answer for this problem. And another interesting fact is that this log n bound is achieved by the simple max mechanism, but only in the assumption that no one is strategizing. So if you assume that people were not strategizing and just saying what they actually think the probability should be, then simple max is enough to get this log n bound. So you don't need that many events, but only when you assume non-strategic forecasters, which, as Andrew shows us, is not a reasonable assumption for real life. But nonetheless, so we tried lots of different things for this problem and eventually came crawling back to simple max because none of them really worked that well. And I don't know, simple max at least achieves this bound in the non-strategic case. So maybe there's a way to make it robust to strategizing in some way. And the proposal is to sort of smooth it out. So instead of taking the actual max function, use the soft max function, which is like regularization in machine learning. So it adds a bit of stability. And what does that mean? So the softmax function, you choose this parameter eta, and you choose a forecaster at random according to some distribution where the probability that I wins is proportional to e to the eta times their total score. So if you imagine when eta gets very large, this approaches just the normal max function, because any small deviation, any small gap between the scores between two forecasters will be magnified multiplicatively until basically you're assigning probability 1 to the highest. So when eta goes to infinity, this is not truthful, as we've seen. But it is selective, so it's choosing a forecaster with very high probability, probability 1. But on the other extreme, so now let's think about the other extreme when eta goes to 0. So here, for small eta, e to the eta stuff is approximately 1 plus eta stuff. You can see this by a Taylor approximation. So when eta is very, very small, the probability of I winning is roughly proportional to their actual total score. Like it's a linear in their actual total score. So if they want to maximize their probability of winning, then they want to maximize their expected score. So you're sort of aligning the maximize expected score with maximize the probability of winning. And so in that case, you do actually get something very, very close to truthful, and in the limit, it's truthful. But the problem is it's not selected. So you can also see when eta is basically 0, the probability that I wins is, well, you have to normalize this. This is proportional to. So the probability distribution is basically the uniform distribution. And that was the problem with ELF. Things were too uniform. So on the one hand, we're very selective and we get this nice concentration bound. On the other hand, we get truthfulness, but no high probability bound. So the question is somehow there a sweet spot in between where we get enough of the truthfulness and enough of the selectivity to sort of get enough of both to pick the best forecaster with high probability? And it turns out the answer is yes. And we achieve this by sort of controlling how badly truthfulness degrades as you increase eta. So something we call approximate truthfulness. And we show that using the softmax function, players will always report within order eta of their beliefs. So they're order eta truthful. And here eta, eta is controlling how selective this is. When eta is 0, it's not selective. When eta is very, very high, it's very selective. So it's saying, well, if you're in the lower regime of eta, then players are pretty truthful. And it turns out that you can then find an eta where they're truthful enough, now that we can control exactly how truthful they are, but eta is large enough that you still get the concentration, the selectivity. And so putting these together, softmax chooses the best forecaster with high probability, given only log n events. So somehow we are able to retain that log n bound from simple max in the non-strategic case. And we just add a little bit of regularization that makes it robust enough to strategizing, but doesn't degrade this bound. Questions? Yeah, Ken.
How would this result translate to Kaggle? If you were to go to Kaggle and change it,
Yeah, so
right? How would this guide that change?
I'll touch on that in about 10 minutes, I think, but just to briefly, foreshadow that, we'd basically be asking them to choose a winner at random, which they don't want to do. So yeah, there is that challenge of, and there are some other ways that you could try to, approximate that using first, second, and third place prizes and things to try to smooth over the max. But yeah, great question. Okay, so I mentioned that thus far we're assuming the events are independent, and meaning that the probabilities of different events multiply. So we're in the independent probability setting, and this is actually something that the entire literature has assumed up until this point. So the ELF bound also assumes this, but when you think about it, it's not great to make this assumption. So if you look at where these competitions are actually being used, like what are people trying to forecast? Well, things like the US election, where we have swing states that tend to swing in the same direction. Time series data, well, nearby data points are clearly correlated. And even in basketball tournaments and other sports tournaments, if there's an upset early on in the bracket, that could vastly change the probabilities throughout the competition. So we have a lot of correlation actually in the events that we would like to predict. But what's challenging is how do we quantify this correlation in a way that's useful in this context? And it turns out that most of the natural things that you would try, like covariance or entropy or all kinds of things, there are counterexamples where those quantities are low, and yet you still can't choose a good forecaster with high probability. So we sat on this for a while, and our contributions are really, I guess the first contribution is just coming up with a way to quantify correlation that makes sense in this context. So something we call BC block correlation. And the B here is like how many events are in, what's the size of a block of events that are highly correlated with each other? And C is like the residual correlation outside that block. And it's a very general definition. So everything, any joint distribution is BC block correlated for some B and C. If B is 1 and C is 0, that's the independent case. So it's a nice like way to quantify correlation that we hadn't seen before. But because it hasn't been out there, we needed a new concentration bound to make high probability statements. So thanks to Bo and Manuel mostly, there's this new concentration inequality that has very non-trivial proof. And using that and the existing approximate truthfulness framework that we can extend to the correlated case, we're able to show that softmax is still accurate even with correlation, but the number of events grows as the size of the blocks grow. But in a sort of naturally, it degrades gracefully in the presence of correlation. All right, and the last thing, I guess it wasn't quite 10 minutes. So to get at Ken's question, turns out organizers of competitions don't really want to choose winners at random, which I don't know is a little silly because the events themselves are random, or so we think. So they're doing it anyway, but whatever. Maybe we're stuck with this simple max thing because, you know, people don't want to do that. Look, in soccer, we choose the winner by penalty kicks. Like, that doesn't make any sense either. Anyway, so maybe we're stuck with a simple max function, but you know, there are some settings where people generally agree that simple max should work well. And one of those is probably the most common thing you see on Kaggle are these large data machine learning data science competitions where the events that you're predicting are like a held out data set of tens of thousands or maybe even millions of test data. And it sort of makes sense intuitively that there wouldn't be much to gain by trying to make predictions on those 1 million data points a little more extreme. But we don't really know why. It turns out that even though this is quite intuitive, when you really sit down and try to prove certain settings where this should work just fine, it's somewhat subtle. Like if all but one of the test data points, everyone totally agreed on what the correct probability would be, then you sort of reduce to the one event setting. So there's something subtle going on, and in ongoing work, we're trying to nail down, like, if you really wanted to use simple max, what are the assumptions under which that could make sense? Yes.
Yeah, I have a question. So you motivated your some of this stuff based on this blog post of the winner from Kaggle. So he was looking at the answer, others, I presume, and you can do that sometimes in Kaggle. You see what the performance of the others. So I wonder if correlation to you means you look at the answers of others, or you get to see similar events and then that correlates you.
Yeah, good question. So correlation, by which we mean is like the outcomes of the events as a probability distribution are correlated. So like two states will go Democrat or Republican with higher probability than you would the product. But yeah, and the other part of your question is, do competitors get to see what each other are reporting? Sometimes you get a leaderboard. In this case, Andrew wasn't actually responding to what people actually submitted. He was just guessing based on past competitions what people might submit in this competition. And I assume because of the way basketball works that you submit all the predictions ahead of time. I don't actually know. But yeah, and here it's even a problem if you're just thinking about what other people might submit. Question, okay?
Reformulation of the question is if you were to rework Kaggle to use the new results. And there was some competitor vendors that didn't have like a model of competitor submissions, simulated competitor submissions boxes. With your new algorithm, you're more likely to select that other person's.
Yeah, so I guess in other words, if you strategize, would it hurt you? I think our goal is that if you were to do all of this work, then what you output in the end is very, very close to what you would have output anyway. So you might get a slight gain, but it shouldn't be much of a gain. Yeah. Okay. Thanks for the questions. So, I promise that's all I wanted to say about forecasting competitions per se, but I promise this connection to learning algorithms that are robust to strategic manipulation. So yeah, let me just set up this very general area, and then we'll zoom way in on one particular problem. So here's the general area. Unlike what you might have been told in your machine learning class, pretty much any time machine learning is deployed in a way that has some influence on people's lives, someone is trying to game it. So there are lots of, by the way, I could not believe that this is a real thing. I didn't even look for this. I just was looking for images of spam, and I learned that this is a real thing. I don't know what the world is coming to. But okay, so like a classic example is spam detection. So obviously the spammers are trying to evade being detected. Fraud detection, plagiarism detection, even things like credit scores, loan decisions. We sort of all accept that there are certain things that you can do to increase your credit score, but does that actually change your credit worthiness? Maybe not. So all of these examples, even things down to, you know, doing things to maximize the chance that my post is seen on some social media platform or my website is viewed. You could think of all of these things as trying to game some learning algorithm out there. And given how widespread it is and the sometimes, you know, large consequences that this strategic manipulation could have on the performance of the algorithm. Oh, and yeah, so what's in common is the inputs to these algorithms are not some like objective data set sitting over here that was collected in the wild, but they're strategically chosen by people that have a stake in the algorithm's predictions. And so naturally, we would like to design our learning algorithms that are somehow robust to this strategic manipulation, that the algorithm will go haywire even under the presence of this strategizing. Okay, so this is a very, very broad area with a lot of interesting work going on. I'm only going to tell you about one particular problem that our work has relevance to, and that's this problem of a classic learning theory problem called online learning from expert advice. So here, it's a very particular problem. You have a bunch of experts, and then iteratively on each round T from 1 to big T, the experts are going to state what they believe about the outcome on that round. And the algorithm is going to choose one of the experts to listen to on that round. So think of this as like the probability of rain on capital T time steps. The algorithm chooses one of these forecasts to listen to. And the algorithm's goal is to perform not much worse than the best expert in hindsight. So after all the capital T rounds, you look at who is the best expert on the actual data that you ended up seeing, and you want your performance to be not that much worse. And we usually cast this as minimizing regret. So this first term is the score of the best expert in hindsight, once you've actually seen all the events, minus the score of the algorithm. And remember, the algorithm is simply just choosing an expert IT on each round T and predicting whatever they believe. And there's a whole, you know, huge literature on online learning, and there are lots of algorithms that you can use to achieve a root capital T regret bound, which is considered good. in this case. So that's sort of the benchmark. So this is the best you can do in the non-strategic setting. So what happens in the strategic setting? Well, now we imagine that our experts are strategizing. They can report something potentially different from their belief. And why would they do that? Well, let's say they're trying to maximize their chance of being chosen by the algorithm. So this is, you know, this is a phenomenon that does show up in a couple of cases, but it's sort of you could think of it as a classic problem with a natural notion of strategizing that theoretically we'd like to understand. And even in the presence of the strategizing, where experts are now reporting things that don't match their beliefs potentially, the algorithm is still trying to, so this is now the performance of the algorithm, so it only has the reports of the experts to go with, but the algorithm is still trying to perform well with respect to the beliefs of the best expert, which the algorithm doesn't even have access to. So we want some guarantee that says you're performing well with respect to the best expert, again, where we define the best expert according to their beliefs, not whatever they said to strategize. And it's been open for a while now to find an algorithm that achieves such a guarantee. There are some results on the so-called myopic case where experts are only thinking about the next round, and then in that round, they only think about the next round. So it's a quite restricted setting. But beyond those works, it was sort of open to find an algorithm for this setting. And it turns out that, so one of the algorithms that achieves this root T regret guarantee is called multiplicative weights, which you may have heard of. And what is that algorithm? It's to randomly select an expert according to the softmax function. And you choose a particular parameter for the softmax function, which is 1 over root the number of rounds, capital T. And using our results on the softmax function, we can basically show pretty easily that this multiplicative weights algorithm will also work well in this strategic setting. So the root T regret bound, which remember is good. It might seem bad, but it's good. It achieves the same regret bound up to order, even in the presence of strategic experts. And since I'm a theoretician, I have to give you at least one proof. Here it is. If you want to fall asleep for a minute, I won't fault you for it. Okay. So here's the proof. Sketch, I should say. So remember, here's the regret guarantee that we'd like to bound. So it's the performance of the algorithm, given the reports of the experts, as compared to the best expert in hindsight as judged by their beliefs. So the first thing that we do is say, well, we know by the approximate truthfulness of the softmax function that the agents will be submitting some reports that are close to their beliefs. And how close? Order eta, which is order 1 over root T. So we can say that this, and the score, by the way, is a Lipschitz function, if you're worried about that. So the reports are close to the beliefs. So the score of the reports is close to the score of the beliefs up to this 1 over root T factor. So now if we're very pessimistic and say we're always adding to the regret by 1 over square root T, summing over the T rounds, we just pull out a root T. Right, so I just pull out a root T from all these plus or minus root T's. That gives me an upper bound. And now what I'm left with is an apples to apples comparison. So the algorithm is given the reports, but now I'm comparing that to the reports of the agents. And just by the classic guarantee of multiplicative weights, which is in this setting where, you know, what the experts say is also what they believe, multiplicative weights gives a root T regret bound for this part. So overall, that gives us a root T regret. Okay, so what have we learned from all this? Well, in the setting of forecasting competitions, we've seen how to design a mechanism that achieves the optimal bound of number of events needed to choose a forecaster with high probability. And it's even robust to correlation. which it's not even clear whether ELF could be robust to correlation, but sort of it's already less efficient in terms of number of events anyway. In online learning, we saw that we get the optimal regret bound in this particular setting of online learning from strategic advice, from expert advice, even when the experts are strategizing to try to be chosen more often. And so, okay, takeaways, even though they won't, probably, Kaggle really should be choosing a winner at random using a softmax or something similar. But also, I think what's, stepping back, what's interesting to me as, a theoretician in this space is that a question that we often ask in algorithmic economics and economics more broadly is, what is the cost of strategic behavior? Like, compare the two worlds where you have a benevolent dictator telling us all what to do in our own best interests. How good is society in that case versus the real world where we're all, just kind of free for all, rushing the line or whatever? How bad is the world? So how much worse does it get given that we don't have someone telling us what to do? And in both of these, so sometimes this is quite large, actually. So in traffic is sometimes like traffic routing is considered a pretty good case, but even there you get like a significant cost to strategic behavior. But in this case, there's basically no cost. We get the optimal guarantees for the non-strategic case, even in the presence of strategic behavior. And I think that's quite fascinating and could shed light on nearby problems where we could expect to get similar benefit. Okay, so let's see, how am I doing on time? Good, okay. So I've told you about forecasting competitions and strategic manipulation in machine learning. Let me tell you now briefly about markets and learning in games. So this markets stuff is joint work with PhD student Manisha and undergraduate researcher Aditya and Bo. And one paper that's been submitted and some follow-up work. And to tell you what's going on, so the title is Decentralized Markets. Let me first tell you about prediction markets. So suppose you wanted to know the probability of some, say, geopolitical event, like the probability that a woman president is elected to the US in 2024. And the idea behind prediction markets is, well, let's open a market and we'll let people buy and sell securities of this particular form called an Arrow de Bruce security. It's a piece of paper, well, not really, but it's a contract that's worth $1 if the event happens and $0 if it doesn't happen. And if you think about it for a bit, if the price of this security is much less than the probability that you think the event will happen, then if you buy it, then you're profiting an expectation. Like you think that it is worth more because you think it's quite likely that this will end up being evaluated to $1 and it's at a lower price than the probability. So the expected value of this is the probability. And conversely, you'll sell if you think the price is too high. And, the conventional wisdom is, well, therefore, the consensus, the price of the market after things settle down should roughly equal the correct probability of this event. And so I pulled this up Monday. It hasn't changed much. It's now a 15% chance, according to the market, that we get a woman president in 2024. So that's the idea behind the prediction market. And long story short, there were some liquidity problems, and to solve them, it was proposed to run an automated market maker, which is a central authority where anyone can come to that authority and ask to buy or sell some securities, and that market maker will provide a price. So always willing to price any trade. And there's been a really large body of literature on how to design such automated market makers that have natural properties that you would like if the goal of the market is to aggregate information, which is the goal of prediction markets. And sort of the high level insight is that you want to design a market so that if you make a trade that moves the price from P to P prime, and then you eventually see the outcome Y, then the profit should equal exactly a difference of loss functions. And what does this mean? Well, it's like you're profiting according to how much you improve the predictive accuracy of the market. So how much you decreased the loss going from P to P prime. And yeah, it's not like totally obvious how you design such a market, but it turns out using convex duality, you can design markets that exactly do this. Meanwhile, there's this thing that's happening in the blockchain world, which is to set up decentralized exchanges for cryptocurrencies and other things. And it's interesting that for different reasons, namely the traditional continuous double auction order book, those sorts of markets that you would see on Wall Street, they're expensive to run on the blockchain. So for this very different reason, they're also thinking about running automated market makers. So a lightweight piece of code that can take trades and price them. And so again, the question is how to design such a thing. And here, of course, the setting is very different. We have cryptocurrencies. There's no outcome. There are no weird contingent securities or anything. But it turns out that you want to design these things exactly the same way that you did in the prediction market case. And I don't have enough time to go into the details, but let me show you an evocative figure, which is that somehow in these markets for cryptocurrencies, it turns out that the trades that are allowed are those that are exactly expressed in terms of a difference of loss functions. So even though there's no outcome here, and the dot here is representing like an amount of a particular cryptocurrency in this vector R, again, I don't have time to tell you the details, but it turns out that again, in these markets that have nothing to do with prediction, or so we thought, there's a difference of loss functions going on. And in fact, Uniswap, the most popular of these sorts of markets, turns out to relate to, it's exactly of this form for a loss proposed in the machine learning literature back in 2005. So I think the most interesting takeaway here is that markets that you just want to be good as markets turn out to you design those in the same way as you would if you were designing a market that was designed to aggregate information. Somehow these things are very much aligned. And we're currently working on leveraging this connection in both of these worlds. All right, and the final thing I wanted to tell you about is learning dynamics in games. So this is joint work with PhD student Gabe, who graduated a couple of years ago, and Georgios from DeepMind and Singapore University of Technology and Design. And it produced these two papers. Okay, so the idea here is, again, a very broad question about how humans or algorithms behave in strategic settings. This is a super broad question, and obviously it has, has relevance in economics and also in AI, things like generative adversarial networks, where we're setting up our learning algorithm explicitly in some sort of game. And if you ask, the dominant theory in economics, well, the answer is simple. Humans are algorithms. They should just play the Nash equilibrium. Just sit down, write down the game, solve for the Nash equilibrium, and play the Nash. There you go, right? And well, yeah, that's not really how the real world is going to work here, right? And for one thing, we know that Nash equilibria are intractable to compute in general, but even if they are tractable in some computational sense, humans aren't great at that. And neither are algorithms if they need to behave, if they need to be lightweight enough, and so on. So an alternative perspective that emerged in economics and was picked up in computer science as well is think about learning. Like, what if humans or algorithms are trying to learn to play as they go? Can we understand the dynamics of learning algorithms in games? And, online learning algorithms that are iteratively trying to choose predictions or choose actions are not necessarily a great proxy for human learning, of course, but maybe it's good enough that we could get some qualitative insights into how things might play out with humans as well. So there's a large literature on this subject, very interesting literature, and it kind of casts doubt at our ability to understand what's going on here. So they show non-convergence results to Nash, cyclic behavior, even chaotic behavior. So the literature was kind of bouncing around in these sort of negative-ish results. And what we were able to do is kind of definitively answer that no, there is no hope of really understanding this in general. Womp womp. And so I'll just very briefly tell you what we showed. So we studied something called the replicator dynamic, which is a continuous time limit of algorithms like multiplicative weights. So we're, instead of finite time choosing things round by round, we take a continuous time limit. So it's nicer to analyze. And we study matrix games, which are very simple games. Well, they might be very complex, but as a setting, it's very simple. Things like rock, paper, scissors, a finite number of strategies. Each player chooses a strategy, and we look up what the payoff is. And through a very complex series of reductions,
So sorry.
no worries. We show that if you give us basically any dynamical system that you might be interested in, then we can diffeomorph, approximate, embed, and get it all the way down to the same as a replicator dynamic on some game. So pretty much any dynamics that you care about, they're approximated arbitrarily well by learning dynamics in some game. And to illustrate this, we came up with an 11 strategy game where if you run the learning dynamics on this game, then you get on some submanifold the classic Lorenz attractor from the butterfly effect and whatnot. So this was like our first result, but then, you know, this is showing that, wow, you can get pretty much any dynamics from this. But then we thought, well, maybe we can say something stronger here. And we were reading about this research program on Navier-Stokes equations, where there is some polynomial system of ordinary differential equations on the 18 sphere that was Turing complete. And so, okay, we can, yeah, and what does Turing complete mean? Meaning that you can simulate a universal Turing machine using the dynamics. And basically by plugging this into our framework, it took a bit of work, but you basically get the same for learning dynamics. So we take these dynamics on the 18 sphere, we convert them into something that works for this, and then plug in all of these reductions to get a game. And so there are lots of implications. I don't have time to get into it, and interesting open directions. I'll briefly mention one open direction, which is, I said this is a large game. It's a very large game. I'm sure you'll immediately recognize this number as 76 choose 18 plus 1. So one open direction is maybe lower that a bit. You know, we get the result, but maybe you can do it with fewer strategies, and discrete time is also quite interesting. Okay. All right, so that's pretty much all I had to say. I just wanted to shout out two problems that I didn't have time to talk about. One is the design of surrogate losses in machine learning. So a lot of work in my group, in our algorithmic economics group in general, is on this subject. So Jesse's thesis introduced this embedding framework, but we've since, you know, been applying it to specific domains and trying to extend it. And finally, since this is a tenure talk, I should brag about something. So this work on elicitation complexity was published in Biometrica and won the Provost Faculty Achievement Award last year. All right, with that, thank you so much for your attention.
We have time for a couple questions, unless they've all been asked. Why is truthfulness a good thing
Truthfulness. Hmm.
in this context?
So true.
In the forecasting competition context? Yes, there are a couple of reasons why you would really hope to have truthfulness. One is it sort of in economics in general, we like truthfulness because it makes everything easier. Like once you get truthfulness, you can do whatever you want because you know that people are saying what they believe. Whereas if you don't have truthfulness, it's just kind of a mess.
Observer problem.
Yeah.
Yeah, okay.
But another reason is that sometimes you run competitions to actually get forecasts. So like in a geopolitical forecasting competition, you might be interested in the actual probabilities of those events. And if people are not being truthful and they're just kind of gaming it, then you don't have good data. Yeah.
All right, well, let's thank Raf again. Well, thank you.